Hi, welcome back to Algebra 2. This is the last lesson of Unit 6, which is 6.12, the locus definition of a parabola. Now, I'd love to spend like an hour talking to you about conic sections and how they are created or where they come from, but I think that's a discussion for pre-calculus. It used to be something we had in Algebra 2, but they moved it out once the Common Core curriculum came in. But a circle has a relatively easy locus definition. We know about locus from geometry, let's hope. We'll talk a little bit about it in the video that we're going to watch, just a quick one. So the circle's locus definition is a collection of all points equidistant from a given point. So if you think of a pencil attached to a rope or attached to a string, also attached, let's say, to a tack, and you loop it around your paper, you get a perfect circle. Parabolas have a slightly more complex definition. So a parabola is a collection of all points equidistant from a fixed point called a focus and a fixed line called the directrix. So I have a quick video here for you, and it might help explain things a little bit, so hold on.
Satisfy one or more conditions.
Well, that was not supposed to happen. Hold on.
In geometry, a locus is a figure that is a set of all points that satisfy one or more conditions. For example, let's say we have a given condition that each point in a locus has to be 4 centimeters away from point A. Well, the figure that represents this locus is a circle with a radius of 4 centimeters.
Which is what we just talked about.
Now let's think about a little bit more of a complex example. A different conic, a parabola. And in the study of conics, we learn that a parabola is the locus of points that are equidistant from a point that we call a focus and a line that we call a directrix. So let's start with an example. So we're going to take this parabola where we already know the focus and the directrix, and we're going to see how the points on the parabola are equidistant from this point and this line. So let's take this arbitrary point. If we want to see how far away it is from this line, we need to remember our geometry and remember that the distance between a point and a line is represented by the segment that is perpendicular to that line that passes through the point. So let's construct that and measure the segment. Now let's measure the distance between this point and the focus. And as you can see, the distances are the same. And as we move this point around in the parabola, we can see that it's always equidistant from the focus and the directrix. So how can we use these properties backwards to construct a parabola from a given focus and directrix?
So that is the question of the day. How do we create an equation given this information? So let's look at a few things first. So exercise 1 says the parabola y equals 1/4 x squared plus 1 is shown graph below with selected points shown. For this parabola, its focus is the point 0, 2, and the directrix is the x-axis. So I'm just going to pull this up a little bit so we can see it. And I just wanted to remember that this x-axis is also the directrix, okay? So this is the line y equals 0. And our directrix for this course will always be y equals a number. It's not going to be, and at most time it will be a nice number, friendly number, as I would say. So we need to recall the distance formula from geometry. Yep, you thought you were done with it, but you're not. So in geometry last year, when you said, when are we going to use this stuff? Your teacher hopefully said, when you get to Algebra 2 and pre-calculus, and even when you get to calculus. So A says, how far is the turning point or the vertex from both the vertex and from the focus and the directrix? So our vertex is right here, and you can see how the vertex is 1 unit from the focus and 1 unit from the directrix. So let's write that down. So the turning point, because that's what the word they use, so let's use that. The turning point is 1 unit from the focus and 1 unit from the directrix. How far is the point 610 from both of them? Well, the point 610 is sitting right up here. So 610 is sitting right up here, right? I guess they could have used 4, 5 as well, but we picked 610. Well, to find out how far it is from the directrix is pretty easy because it's a straight line straight down to it. And because the y-axis is our directrix, we know that our units is going to be 10. Now, if our directrix was below the y-axis, we'd have to add a couple, and if it was above it, we'd have to subtract a couple. I'm going to look at a couple of examples like that a little bit later in the lesson. So we can basically say, okay, 610 is 10 units from the directrix. Now, based on what we just heard in our video, when we determine what the distance is between the focus and the point 610, I am thinking that it should be the same distance from here to here as it is from here to here. And it looks pretty good, but we can't always trust our pictures. So let's look and see. So how would you find the distance between our 2 points, 6, 10, and our focus, which is 0, 2? Well, we use our distance formula. So distance is equal to the square root of 0 minus 6 squared plus, so it's kind of the opposite of doing the slope formula. You start with the x's. And it doesn't matter. You could start with the y's because it's addition and we could commute them. So 0 minus 6 and 2 minus 10 squared. So this is equal to the square root of 6 squared is 36 plus 2 minus 10 is negative 8 squared, which is 64. Beautiful thing is when you square them, they both turn positive. So this is equal to the square root of 100, which is equal to 10. Yay, that's what we need. So we can basically say 6, 10 is also 10 units from the focus. Nice. So that basically, again, talks about what the definition of a parabola is. The directrix and the focus have always been there. They're just always a little bit invisible, and we haven't really talked about them until now. So hopefully the next time you decide that you're going to graph a parabola, you'll be thinking about, gee, I wonder where the directrix and the focus would lie. Okay, so any line and any point not on the line when used as the focus and directrix define a parabola. The most challenging type of problem we will tackle in this course will be finding the equation of a parabola whose focus point is not on one of the two axes. We will, however, stick with horizontal lines as our directrices. All right, so, but like I said, so we're not going to do vertical lines because that would be square root problems, and then there's a whole bunch of stuff we have to consider. So let's just move on to our next example. Finish what you're writing down, and then we'll move on. Okay, so now you don't have this little graph on your page, but I put it on mine. You can just draw a picture, or you can always take a little piece of graph paper and tape it in if you want to. I'm going to always remind you, you will always have graph paper accessible to you. You'll have it on the Regents exam. You'll have it in my classroom. So if having a small piece of scrap graph paper is helpful to you, just ask for it. So exercise 2 says determine the equation of the parabola whose focus is 0, 4, 0, 4, and the directrix is the line y equals 2. So first of all, just to be able to graph the curve, I know that my turning point has to sit halfway between the focus and the directrix. So I know that this point right here, which is the point 0, 3, has to be my vertex. And because it's really, really close to my focus, I know it's probably going to be a little bit wider. So it's going to look something like this. Again, let's not trust the pictures, especially mine. But that's kind of what it looks like. And when you visualize it, it makes things a little bit easier. And when you have to find that vertical distance, it's also really helpful to visualize it. So now they want us to create the definition. So the equation. So the equation we're going to take right from our distance formula, because we know that the distance between a point, any points. Now this one, I don't know if this particular point, I'm going to call this point x comma y because I don't know exactly what it is. And I'm going to figure out what the vertical distance is between here and here. Now I know that the distance from here to here is y. We found that out in our last example. So if I know that this whole thing is y, how much do I have to subtract out in order to get the distance from the point to the directrix? So this is 2 units right here. So I'm hoping you see that it's going to be y minus 2 is my vertical distance. Let's do something first. Hold on. Let's say, what do we need to find? Let's find the distance. How did I write this? Let's say the vertical distance. So the vertical distance between y and the directrix. So that's what the left-hand side is. So the vertical distance from the point to the directrix in this case is going to be y minus 2. So if it's above the line, you're going to subtract out how long it takes you to get down to the x-axis. All right, so that's going to be y. So in other words, if by chance this was 1, 1, 2, 3, 4, 1, 2, 3, 4, 5. So let's just say this was the point 4, 5. I know my distance from here to here, like shown in the purple, would be 3, because it would be 5 minus 3. But like I said, we're not going to be that specific. I'm just saying it as an example. So the vertical distance has to equal the distance between my given point, xy, and the focus. And in this case, the focus is 0, 4. All right, so this is equal to, now this is where your distance formula comes out. It's the square root of, okay, what are your 2 points? XY and 0, 4. So I'm going to put the x first, and I'm going to say x, I want the 0, I want the red, x minus 0 squared plus y minus 4 squared. And the nice thing is whenever we do this, we're always going to have x and y being the first point. So we're going to use x and y first. All right, so the distance formula says it's the difference of the x and y, the sum of the 2 differences squared. All right, then we take the square root of it. But let's just simplify it a little bit first. So this becomes the square root of x squared plus y minus 4 squared is equal to y minus 2. Now, how do I undo a square root? Square both sides. So I get y minus 2 times y minus 2 is equal to x squared plus y minus 4 times y minus 4. So far, so good? So I get y squared minus 4y plus 4 equals, just multiply them out, x squared plus, multiply this piece out right here. This becomes y squared minus 8y plus 16. And what we're going to do is we're going to move the y to one side because we want this in the form y equals, and everything else to the right-hand side. So in this case, almost always, in your case, probably always, your y's are going to cancel out. When you have the same value on both sides of your equal sign, they can cancel out. Because if I subtract y squared from both sides, they cancel to 0. So I'm going to leave the minus 4y there, but I'm going to bring over the 8y to visit it. So positive 8y plus 8y. And I get 4y plus 4 is equal to x squared, these canceled, plus 16. I'm kind of running out of room a little bit here. So why don't we just bring the 4 over, subtract 4 from both sides. I'm going to bring it up here. And I'm going to get 4y is equal to x squared plus 12. And simply divide both sides by 4. Divide everything by 4. And my final answer is y equals 1/4 x squared plus 3. I like to read. You could write it as x squared divided by 4. I'm kind of a girl, like when you talk about a parabola and a vertex, a focus, the 1 over 4p that's in front of the x squared has value. So we usually write it as a fraction in the front. But if you wrote it as x squared over 4, they are equivalent statements. So kind of cool, right? They are kind of fun once you get to know them. So finish writing up what you need to. And I want to take the next one, exercise 3. We're going to take it step by step, and I'm going to see if you guys can stay with me. All right, so I'm going to be asking you to pause it from time to time just so you can try it, because this is all we're doing for today, just this last exercise, and before you start doing it in class. And like I always say, if you have any questions or you want me to go over any of these in class, I am always happy to repeat it. Sometimes it's nice to have the live version so you can ask questions. So take a look at exercise 3. Same type of question. Determine the equation of the parabola whose focus is the point 4, 1 and whose directrix is the horizontal line y equals -3. Once again, I like to start with a picture because it just makes things a little bit clearer for me. All right, so 4, 1, 1, 2, 3, 4, 1. So it's a little bit off to the side this time. And my horizontal line, my directrix is y equals -3. So it's down here. So in order to complete my picture, I have to realize that my vertex is going to be halfway between it, and it's going to look something like this. Now, I can't do the other side, but that's okay. So in order for me to do this, so again, I'm going to remind you that on one side of the equal sign, we're going to have the vertical distance from the point to the directrix. And on the other side, we're going to have the distance, and put the 2 points down. So from xy to the focus, which is at 4, 1. Now, pick a point. Doesn't matter where. Here's a point. We're going to call that point xy. So what we're saying is the distance from here to here and the distance from here to here. Now, I know my y in this case. Now, again, I kind of picked it so it's on a lattice point, but I didn't mean to do that. My distance from here to here is that y. So this time, because my directrix is below it, how many units below it is it? It's below it by 3 units. So when the directrix is below the x-axis, you have to make sure in your vertical distance, you're adding whatever that distance is. So my vertical distance is going to be y plus 3 this time. And my distance from x to y to 4, 1 is my distance formula. And it becomes x minus 4 plus squared plus y minus 1 squared. So for a distance formula, it's not too hard to remember. If you remember the first point is x and y, you're just making sure that you're subtracting it, just like we always do. Remember, it's always a different sign inside from our point that we're given, and this is no different. All right, so it's always the opposite sign. So it's x minus 4 and y minus 1. And now simply we're going to solve it. And again, this part is a geometry question or an algebra 1 question. The hardest part from algebra 2 is just getting to that part of the equation. So this part now, we're simply going to square both sides because we need to undo the square root. We square both sides. And when we square both sides, we get, and please don't skip this step, we get y plus 3 times y plus 3. Great, sorry about that. Equals x minus 4 y plus, just keep going, duh, plus y minus 1, y minus 1. All right, so when you're multiplying squares, it's not so hard because you simply are going to be multiplying the first term for the y squared. You add the plus 3, and the plus 3 is plus 6y, and then multiply the last ones plus 9 is equal to, the same thing goes here, multiply the first term, add the last term, so it's minus 8x, multiply the last terms to plus 16, and then do it again. Plus y squared plus 2, I'm sorry, minus 2y plus 1. And then from this point, the y's get to the left, the x's go to the right, and the numbers go to the right. So the first thing we're going to do is, again, here's a y squared and here's a y squared. They will always go out because in a parabola, the y is not squared and the x is. So those y squares will always, not even almost, always cancel each other out. So what's the first step? Let's do a little more cleaning up. Now I only have 1x squared, I have minus 8x, I have minus 2y, and I have a plus 17 because I'm going to add these two together. So let's move the 2y over. And the more you do of these, the more consistent you become and how you solve them. So 8y plus 9 is equal to x squared minus 8x plus 17 minus 9. You could do that in one step if you wanted to. So 8y is equal to x squared minus 8x plus 8. And now divide everything by 8. So my final answer is y equals 1 over 8 x squared minus x plus 1. Beautiful. So, super fun, right? So, if you want to, you can continue on, get some, maybe do one of the independent practices. I said I was going to stop and pause and let you do some. I guess I forgot to do that. Kind of just worked all the way through it. But I think that, like I said, if you were to do a few more of these, consistency, like I always seem to cancel out the y's first. So if you just kind of look at the way I do things here, if you, the first things I usually do is I multiply them out like I did here. All right. Then what I did is I kind of cleaned it up a little bit and I combined like terms. And then at the same time, I got rid of those y squares. All right. I moved the y over to make sure that's all by itself. I move the 9 over, so now the y is isolated on the left-hand side. And then divide through whatever the coefficient is in front of the y to finish up our equation. So I went a little over my time. Sorry about that. But I think it was totally worth it because I think that little video might have helped you really understand and see it. Um, Again, if you need graph paper, feel free. I'll give you some. And if you don't need it, then just draw the little graph. Because half the times when I do it, I don't even draw the graph. I kind of wing it. So for example, I'll do something like this off to the side. I'll say, well, here's my graph, and it said x is -3, so it's down here. So 1, 2, 3. No, it's y is -3, and the point, let's say, is up here somewhere at 2. So I know that 1, 2. So I know my vertex is in between it. So it's going to look like this. So I'm able to kind of do it without even having to use the graph paper. I can kind of just visualize it with just a quick sketch. But whatever works for you, okay? So always make good choices, and I'll see you next time.